Okay, so pleasure to be here today.
You just have to use the arrow keys. They won't talk immediately. Sorry.
They are talking.
Oh, they are? Great.
Yeah. So I'd like to talk a little bit about some of our projects that have to do with robotics and try to draw some interesting connections between robotic systems and architecture. You know, in the last couple of years, I'm seeing more and more connections between robotic systems that move and react and sense and compute, and architectural systems that used to be static, but increasingly are involving a lot more of those computational elements. So in particular, I'd like to focus on this idea of self-reflective systems that think about themselves and reach conclusions and change their behaviors based on how they perceive themselves. Now, this might sound a very abstract idea, but it's something that we do ourselves all the time. We think about ourselves, we are aware of ourselves and our interactions, and we change our behaviors. Increasingly, we're seeing that in robotics, and where will that take architecture as well? So our background is in robotics. We make all kinds of robotic systems, not necessarily useful robotic systems that can work in factories and so forth. Instead, we make all kinds of robotic systems that allow us to explore these ideas of machine learning and construction. So we make machines that walk, machines that fly and crawl, and I'll get back to how we design these things and how they emerge over time. The main idea that I'd like to present to you, and I'll come back to this multiple times, is that what is happening in the last couple of years, and I think it's accelerating, is that complexity is becoming free. Meaning that while it used to be the fact that you wanted to make something that is more complex, had more details, had more features in it, it used to be more expensive. New manufacturing technologies are making complexity increasingly less expensive. So, for example, with 3D printers, as you very well know, making something that is complex costs the same in time, in processing, and in kind of features as something that is simple. It doesn't take any more time to print something complex than it does to print something simple. So complexity is essentially free. That is true also for computation, and that is leading to a change in the design space that we can explore. We can explore things that are much more complex, both in their mechanical and structural form, and also it leads to introduction of new kinds of designers. So we have a new design space and new designers. In engineering, we see this all the time. People who are not necessarily trained engineers are designing things that outperform what engineers used to design just a few years ago. So we have new kinds of designers, hobbyists, artists who are doing engineering work, and we have new design space that is easier and easier to explore. And these things are leading to a lot of interesting things, new kinds of representations and new tools. So I'll come back to that, and I'll tell you a little bit about where I think things are going. But let me first tell you a little bit of my own story in this area of robotics. Our lab focuses on robotic systems that adapt over time. Now, this is very, very different from traditional robotic systems that work in factories. Most robotic systems today are hidden from the eye. They work in factories, like this robot over here that works very well. It's superhuman in almost any way you want to measure. It's fast, it's precise, it's powerful, it works 24/7, but it can't adapt. That's its weakest point. So if you think about a robot like this, it will work well as long as everything is in the right place and the right time. But the moment something is missing, it's game over. If a bolt falls off, it cannot improvise. So this is 99% of robotics today. But the question is, can we move to other robotic systems that can adapt? This is looks different on this computer than on the display. Okay. So, let me go back.
Can we bring up the... Sorry. Just happened?
Computer locked.
I think so. Sorry about this. Okay, I have no control over this computer.
Never use somebody else's computer. Ask for assistance. That looks like a good idea.
Nice.
Goes well with your story.
Yeah.
Goes wrong,
There we go. Okay.
you said that.
I think the mouse is not working.
Digital binary system, which is not only 0 and 1, it's a multi-degree. Intrinsically stored right now.
Yeah. It locked. We can't seem to see it.
It was working all right. Voila.
And his videos are not showing properly.
That happens frequently on a video transfer, which is why we ask to bring your laptop. No, it doesn't like you at all.
He brought up his laptop.
That one?
Should I pull this off?
Yeah. Might as well. Put it, dump it back to mine. Excuse me. If you'd like to sign in, please. Okay. Have you got sound?
I do.
Where's
Do
your
some.
Okay, you're on screen. I'll just shut the projector down so you can do what you like. And let me know when you're ready.
Mm-hmm. All right, so we're looking for adaptive robotic systems, and a while ago, this is about a decade old, we started looking at using evolutionary algorithms to design both behavior and structure. And these are examples of two robots that we we basically took a lot of components of robotic systems, bars, joint, wires, neurons as in neural networks. We threw them into a big gaming simulator, and we evolved robots, machines that could crawl across the table. So after a couple of thousands of generations, we got these interesting machines. It began with just random pieces of junk that didn't do anything. But after a couple of thousand generations, we got these interesting kinds of machines. When you look at these machines, you have to remember again that they weren't designed explicitly. They're just a process of this evolutionary process that puts all these components together and generates these systems. Here are these two robots actually 3D printed and working in reality. So that was back in 2000. And here's a close-up of one of these robots, and you can see evolution takes advantage of these very interesting, intricate structure that can only be manufactured using 3D printers. So that was back in 2000. We got on the front page of New York Times with those robots. You can't do that today, but back then you could still do those kinds of things. And the question was, how far can we push this in terms of complexity? So one of the next projects that we did was to try to take this idea of evolving behavior and put it on a much more complex robot, a robot that's not just a few bars connected with motors, but in this case 12 pneumatic actuators connected in a complex way, and this is all driven by a paintball canister in the center, a high pressure canister. There's valves at the bottom right there that control how these pistons expand and contract. And the question was, can we use this process to make this robot behave in interesting ways? Now, what's interesting about this particular machine is that it's very powerful. In principle, it could jump up in the air and do loops and so forth. It's a very high energy machine because it's based on compressed air. So we put this machine in a big cage. We put a camera at the top that watched how this robot behaves. And then you see at the top right the camera view that shows you how what the camera sees. The camera actually looks only at the red dot, which is kind of one of the balls in the robot. And it rewards controllers for their ability to move forward, to make this robot move forward. So basically we had like a rodeo show with lots and lots of controllers taking turns on this robot, trying to make it move forward. In the beginning, they do nothing, but after a while, the robot begins to move forward. So here's a playback. Okay. So you can see here a playback of some of these behaviors. In the beginning, it doesn't do very much, but gradually it's learning how to walk based on the experience that it's learning. Nevertheless, when you look at this, you can see that we're not going to take over the world anytime soon with this kind of robot. It's learning how to walk, but it's very slow, and neither was I going to get tenure in the mechanical engineering department making a robot like this one. So the question is, how can we push this, make it learn a bit more? So I showed you two projects, basically. The first project, we evolved everything in simulation. We then took the best machine that we had, we built it in reality. But that only worked for very simple machines, because in practice, we have the problem of crossing from simulation into reality. The more complex the system is, the more difficult it is to move from simulation to reality. The more dynamic it is, the more difficult it is to do this kind of transition. Any engineer will tell you that with high nonlinear dynamics, you can simulate to your heart's content, but it's not going to transfer into reality. It works well for static structures, not for dynamic structures. In the second project I showed you, we evolved everything on the physical machine itself. We avoided the need for a simulation altogether, but the challenge there was that it took too long to evolve. And again, if you're doing evolution or optimization on an active system, you know that there's a limit to the number of trials that you can do. When we evolved these robots overnight, we could do maybe 100, 200, 500 trials, but that's not enough usually to do any kind of sophisticated optimization. So either we rely on simulations. Simulations don't necessarily scale, or we do physical trials in reality, but these are too slow and expensive. So what can we do? And this is kind of a conundrum that's typical of a lot of these optimization problems in engineering. So we ended up coming up with this kind of hybrid approach, which is really what I want to describe to you. The idea is that you start off with some kind of simulator of the system. I'm putting simulator in quotes because it's going to be a bad simulator, a simulator that's not very accurate. From there, what we did is we took that bad simulator and we used it to evolve robots. We then took the best robots that we got, and we built it in reality. Now, the simulation is bad, so the robot that we built did not work in reality very well. Nevertheless, we had the robot collect its sensations, its actions and its sensation, its motor commands and its whatever it can sense, let's say accelerations and so forth. And from that data, actions and sensation, we can now evolve or breed or optimize better simulators. Okay, so we started off using a fixed simulator, evolving robots. We took the best robot, we built it in reality, we collected data, we used that to evolve better simulators. Now we took the best simulator that we have, we use it to evolve even better robots. We take the best robot that we have, we built it in reality, it's the second one. We try it out, it's probably not going to work well still, but we're going to collect data, use that data to breed even better simulators and so forth. So we're doing very few physical trials. We're breeding a lot of simulators and robots. And in fact, we're doing a kind of, if you like, a co-evolution of two things. Instead of just optimizing one thing, the artifact that we want to build, we also, at the same time, co-optimize or co-adapt predictive simulators that learn from the experience of the bad designs to make better predictions for the future. So you can think about this as a kind of antagonistic co-evolution, predator-prey, if you like, two things, maybe teacher-learner, two things kind of competing, cooperating, and moving forward in interesting ways. So let me show you how that works. This is the final robot. This is a four-legged machine that needs to learn how to walk. It has 8 motors, 2 on each leg, one at the hip and one at the knee. And it needs to learn how to walk. It also has 2 tilt sensors that tell us how it's tilted left and right, forward and backwards, all right? So 8 motors, 8 actuators, 2 sensors, tilt sensors. Now what's interesting about this particular robot is that it has no clue about what it looks like. Okay, so it doesn't know that it's a spider type robot. It doesn't know if it's a snake, it's a spider, it's a tree. Has no clue what is the topology, how the pieces are arranged. And yet it needs to learn how to move forward. So to understand what that means, imagine yourself for a moment in a black box with no windows. All you have are 8 knobs. And as you turn the knobs, you can feel the box tilting left and right, forward and backwards. And you need to make that box move. How would you do that? So you could do that by trial and error, but maybe there's a better way, a more systematic way to do that. So we're going to take that idea that I just described and apply it to this robot. So we're going to have the robot, first thing it's going to do is going to do random motions, randomly activate the motors, and then it's going to create lots of hypotheses, lots of models, lots of simulations, if you like, lots of self-models that describe what it thinks it might be. Now, you'll see this in the movie in a moment. You'll know that all these models are wrong because you happen to know what the robot looks like. But insofar as the robot knows, these will all be valid self-images, self-models, because they will all match correctly with the experiences that the robot made. So the robot might, it will create all these models. The next step, and that's in the green box, and that's the critical step, it will look for the action that causes the most disagreement between predictions of competing models. Okay, it's a bit like a scientist designing experiment that makes two theories disagree in their predictions, because then the result from the experiment will refute at least one of those theories. Okay, so in other words, the robot creates self models, that's a simulation, and then it creates actions to cause disagreement between these models until it can get the model right. It will then do that action, get data, refute some of the models, and so forth, keep on going in a cycle, doing relatively few trials, lots of computation. When the model converges, it will go down to the bottom right, and we can tell it, let's say, find an action that will make the robot move. It will find a pattern of actuation that makes the model move forward, and because the model is close to the real thing, to reality, what makes the model move forward will make the robot move forward as well. So here's an example of one of our first runs with this robot. When you do robotics, you always have the camera rolling, because you never know if it's the last time a robot's going to work. So here it is, unplugged itself. That's it. That's the end of this one. So we replugged it again. We tamed it down a little bit, and here's the robot learning a bit about itself. Here's its first random motion. These are all its self models that it's creating. You can see they're all wrong, but they all make the block in the center tilt in the same way. So insofar as the robot knows, these are all valid hypotheses about what it is. Here's the second, the 8 out of 16 trials. It's beginning to figure out it has 4 legs, doesn't quite know where and how they're attached. And this is the 16th out of 16 experiments it's doing on itself. And it pretty much figured out what it is. It didn't get the placement exactly right, but it's close enough. Using that self-image, it's figuring out how to move. We were hoping to get an evil spidery walk, but instead, we got this lame way of moving forward. But when you look at this robot, you have to remember a couple of things. You have to remember that this robot was not programmed to move. It did not have a model of itself, nor did it do trials of walking before this. Right? So based on the brief interactions with the environment, it created a model of itself, a simulation, if you like, and then it used that simulation to figure out how to walk in what we call kind of one-shot learning using that model. So here's we did something very cruel. We removed the leg of the robot, and we watched what happened. So within about a day, the robot's self-image also loses a leg. As you can see the pink there, it doesn't quite lose a leg, it just makes it very short. You can see the small nub there at the end, and it figures out a new way to move forward, okay, without this leg. Now, granted, probably I could design a better way for this robot to move without a leg, but the whole point here is that it was not that the leg came off, there was a sensor that sensed that the leg came off, and then it switched to plan B. It wasn't like that. What happened, the leg came off, therefore the dynamics changed, therefore the self-image changed, therefore the behavior changed, right? So we're after adaptation based on this idea of self-reflection, and this is what's happening here. So just to give you an idea what happens with 30 independent runs, this is the red dots are what the robot does with a random controller. The black dots are where the robot thinks it's going to get to using its self-image, and the blue dots are where it actually gets to in physical reality. So as you can see, like anything else in academia, this robot has an inflated self-image that tells it that it can do twice as much as it really can. But nevertheless, that self-image, even though it's wrong, it allows it to make the right decisions. All right? So it allows it to make decisions and optimize correctly. So it's an interesting kind of issue that self-models don't have to be correct. They just have to rank options in the right order. So you can take this in lots of different directions. What we're doing now is making robots learning not about themselves, but about other robots based on observations. And then you get interested in things like deceit, cooperation, competition, all kinds of things that you see in animal and human behavior. So let me go back and now put this into a larger context. We have, as I said, engineering, architecture are all experiencing this trend where complexity is becoming free. Making complicated things is not that expensive anymore. And at some point, making complicated, at least with 3D printing and software, complicated things are just as easy to make as simple things. A block with a hole is just as cheap to print or expensive to print as a block without a hole. Okay, so complexity is free. New design that leads to new design spaces, new designers, new representations, and new tools. And if you look at the history of representations, I think we're gradually going down this list of different types of representations, from direct representation all the way down to self-reflective representations. I'll go quickly through those because I think you'll notice, we are probably doing different projects at different stages, but I think this is the trend and where things are going. There are also new tools that involve natural interfaces, applications, and evolution, and kind of compilers, which we've seen before. So just to put this in context, the kind of direct representations are, fixed blueprints, and that's been the nature of engineering and architecture for centuries. People just draw something, and that blueprint basically represents the design in a fixed way. So that's 99% of our history. Then came parametric models, I think, which are kind of the next step. Parametric model in engineering, I think maybe in architecture it's used a little bit differently, but in engineering, parametric models mean models that are adjustable, models that have some parameters that are attached to certain geometry. So you might have the staircase and might have parameters like the length and width and height of the stairs, and the number of stairs, the size of the landing, and so forth. You can tune all these parameters there, and the model will change, and then you can connect it to optimizations and so forth. So this is parametric modeling, and that's been around since the early 90s, and it's been used extensively and kind of replaced fixed representations. The next thing in kind of this progression of representations in engineering are algorithmic representations, and these are basically ways to go beyond parametric to represent object as functions. And what you can see here, this is a classic example. You want to build this kind of thing, you can point and click for eternity to make this, or you can drag and drop in Rhino for a long time, or you can just type in an equation that will produce this. So it's much harder to do to come up with the equation, but if you can do that, basically creating models becomes like programming, and you can make these fancy kind of structures, repetitive structures, and so forth. I think this was done in Loughborough, close by here, and so forth. Beyond, the next thing after kind of programmatic representations are generative representations. Again, I think we sometimes use these terms indifferently, but at least in computer science, we like to think about generative as something that comes out of a series of rules that are applied in a context-free manner. So what does that mean? A generative blueprint is a combination of a seed and a set of rules. So here, for example, two rules, A goes to B and B goes to AB, two simple rules, and I throw in a seed, A, and these two rules and a design applied in a context-free manner. In other words, like a bag of rules applied anywhere that they are relevant will generate a design. So the A, according to rule 1, will go to B. B, using rule 2, will go to AB. Now the A will go into B, the B will go into AB. Okay, just using these, applying and reapplying these rules over and over again, I get increasingly complex structures. So these very simple two rules at the top plus the seed give me this interesting structure at the bottom. So this is what we call generative design. It's context-free rules, and it's very different than parametric design, which is merely kind of adjustable parameters, adjustable design. So all of these things you can subject to optimization, so don't confuse this with optimization. So that could lead to complex shapes if you have rules that instead of A and B, you have rules that have to do with shape, like a circle goes into a square goes into a circle and a square, then you get, let's say, interesting shapes. You throw in a seed and you get something that grows out of it. Beyond that, we have kind of reactive designs that react to their environment. And here it becomes a little bit more abstract. There's all these reactive walls that you see around. You have robotic reactive systems, but you can imagine that these are, for example, you can imagine a lamp, and this is just an illustration. It's not an actually reactive lamp, but it could be. You could imagine a lamp put in a simulation, and it adapts, it reacts to its environment, to the amount of light that it senses, and optimizes itself, let's say, so that it illuminates a room in a uniform way. So you basically, what you do is you put this lamp with the target behavior, and you just allow it to react to its environment, and it adapts until it gets the illumination exactly uniform. So that's you can imagine that as a reactive blueprint. All that information would be in the blueprint, and wherever you put that lamp in a CAD system, the lamp will look different. Every room you put it, it will end up looking different, even though it's the same blueprint. And that's very much, again, like a plant. If you like a plant, wherever you put it, it's the same program, but wherever you plant it, it comes out differently because it's reactive to the environment it's in. You can, of course, imagine dynamical blueprints where these systems interact with each other. So it's not just one blueprint, but multiple blueprints interacting with each other. Again, like an ecosystem of plants that make shade on each other, and therefore they grow in different directions, and some become tall, some become short, and so forth. And that's kind of what we're trying to do with these robots, and so forth. One of the questions you might be thinking, okay, how does this apply to architecture? This is all well and good for robotic systems, but what can we do with architecture? And just want to give you this last example of this is a bridge that I cross every morning walking into Cornell. In fact, it looks like this most of the time. And when you walk across this bridge, you have some time to think what would happen if something in this bridge wouldn't be as strong as it needs to be. And so we thought, okay, let's try to apply this kind of reflective system to this bridge. And the bridge is a very static thing, so how can you apply this self-reflection to a bridge? And the idea is very simple. We did this in simulation. We put these small vibrating elements on the bridge, and we put the bridge vibrates in different ways, and then it senses vibrations in other locations. And again, from this relationship between action and sensation, it can come up with models of itself. And then then it can cause more vibrations to disambiguate self-models and so forth. And we showed that this bridge indeed can model itself and can find out the weak element a lot faster than traditional civil engineering methods. So bottom line is that you can think about different kinds of representations, moving from very static blueprints through parametric blueprints, through generative models, reactive models, generative models, dynamical models, and finally self-reflective systems that keep modeling themselves. You can imagine in the future that we will have buildings that gradually from their experiences build up a self-simulation, and using that self-simulation they can be better buildings. And you can apply that all the way from static structures like a bridge to a whole city. Thank you.
Thank you for that great presentation. Just a little small thing. We're going to take a minute while we switch microphones and technical doohas, but just 1 minute. And also, we had a technically difficult first session, but we're hoping that maybe the next 2 sessions will be better and everyone will be more on time. Thank you. One more thing. I'd like to invite our guests to come and sit with us, and we're going to have a little chat, and hopefully We'll have a little bit more time at the end for questions. If not, we have at the end of the day a session where everyone can ask all our guests whatever they want. Thank you.
Thank you.
Is the mic working? Yeah.
Yeah, it's working.
Okay, so we're going to go ahead and start our first discussion. And we would like you to talk into the microphone, please. So we have a few questions for you that sets out sort of a sequence that we would like to talk about. But going through your presentations, they were exciting, really exciting. And so we're going to start out with questions from the presentation and then move forward from that. I have a question for Luca. The animation that you had where the instruments, each of them had their own bubble and the bubble was moving up and down. So now you have the geometry of the bubble that's coming out of the geometry in the direction of the actual instrument. But when you come and want to actually document it, do you document it through equations, or do you start finding different ways of actually putting that on paper?
Many people tried before to put it on paper, but let's say that I think now it's the time that we should get rid of paper in a way.
Yeah.
So I mean, with all this fantastic equipment we have, that sometimes they don't work, but still they give us a lot of opportunities in order just to use as much real data as we can.
Yes.
And I mean, in terms of that video, it was really simple, because basically I was playing the sound and I had 8 tracks. And basically, I don't know, when you listen to your stereo, you have the volume control that's going up and down.
Yeah.
And that was the same thing. Basically, I had kind of 8 volume control distributed in the space. And basically, I was just wrapping around a shape, a surface. But in theory, it was the same concept of your stereo when on one line you have the volume going up and down. It was just extended in 3D.
Okay. This is why I understand that paper is sort of dying, but this is why we're asking the question. We are PhD students and we are dealing with this all the time, and the same question goes to Had. And when you have this robot that's, you know, growing up, it's a little baby that's kind of learning how to walk. Scientifically, if we want to put this sort of we're doing a PhD, so it has to be a book in general. And obviously we can have more information, but how do you kind of document this growing up, or this starting to become aware?
Why do we need to document
No,
it?
yes, that's why. That's a good question. Well, the reason that we are trying to look at this in this symposium is that we are starting to follow in your footsteps or whatever, but we need to start with paper and then move forward, in order to kind of become distinguished as possible. So that's why the question is like that. I understand that we can document through video, but so you don't use paper. That's what I'm. Is that
No, so
your answer?
the whole point, if you look at documentation, the early documentation was paper and was very static. It just describes the shape and the form, and that's it. It was very static.
Yeah.
As you move with it to these more complex systems, documentation is not static anymore. It's a program.
Yeah.
Okay, a program might be, the code might be static, but the shape it describes is different.
Yes.
You can have a very small program describe a very complex thing. So, and then you move to dynamical systems. You can have a program that describes a complex thing that ends up looking different depending on where you put it, all the way to these reflective systems that they not only do they become different, but they also create a model of themselves which they use to decide. So the level of representation, you can think of paper as a representation. It's a very static representation,
Yes.
and that's kind of the first of a whole series of representations. And you can do so much more if you move away from these static representations to more dynamical kind of representations like programs and
Yes.
self-models. So
Okay.
self-model, the way you think about yourself right now can't be put on paper. It's something much more dynamic, and that's how robotic systems, and I think in the future structures will also be.
Okay. So,
I have a question to Dr. Lipson, because here is Architectural Association. We need to talk about architecture. I'm not sure, but what is the difficulty of architectural robotic things different from the robotic, just a robotic? Do you have any idea?
So the difference between architecture and robotics, I think, you're asking a roboticist, so architecture looks bigger,
Yeah.
and it's more difficult to move it. But but basically, you still have structure. You still have the opportunity to embed sensors and actuators. Now, sensor and actuator in a robotic system is often a motor and accelerometer. On a building, I don't know what sensors and actuators are. It could be, have to do with energy, with airflow. It could be, it might have to do with the acoustics. There's definitely sensors and actuators and acoustics there. There's lots of different sensors and actuators. But if you think about structure, sensors, and actuators in an abstract way, robots and buildings are similar. They're just different scale, different set of sensors and actuators. And the same thing we do with robotic systems, you could do also with architectural systems and even cities. I mean, it goes on all scales, from a lampshade to an urban environment that also has sensors and actuators.
Mm-hmm.
But that's a robotics perspective. I'm sure that there's different ways to look at it.
Can I do question too?
yes, of course.
It was interesting for me the fact that the robot was learning its self-image. So my question was, have you ever tried to compare a computer trying to get a self-image of itself and a person trying to pressing the knobs and thinking,
Yeah.
what's my shape, what am I?
Yeah, no,
to see what's the approach and the difference.
That's a really good question. Nobody knows how babies learn about themselves, and how they experience the world and form a self-image. But you could do an experiment where a human is trying to learn about a robot.
Yeah, maybe you need to move, but
Yeah,
you get
yeah.
the feedback that you're kind of doing something, but you
Yeah,
don't know
yeah,
if you have
yeah.
legs or
Right,
stuff like that.
right.
Yeah.
So it could be. So I don't know. I would imagine that humans are better at it in some areas when it's close to their own image, but it's very difficult for humans to do it with arbitrary, for a building, for example, which has a very different shape and form. But for example, I was thinking when you were talking that it could be applied to your system. Right now, you use a fixed simulator that you manually put in the shape of
Yeah.
the building, But you could imagine that you could just throw a couple of sensors around the room and have a robot or a speaker make lots of sounds, have the sensors pick up the sounds and gradually create a simulation of
That
the
reacts
building
to the
that learns from the
environment.
way that the action, the noise and the sensations, the microphones interact, and will make different sounds in order to disambiguate competing models, and gradually you'll learn to simulate the system automatically. So in other words, you'll have a self-learning acoustic model.
Yeah.
So there's lots of different ways that this can be applied, this idea of self-modeling, not just for robotics, but that's my point.
That's really cool. I lost my train of thought. Okay. So we're gonna ask a few questions about cognitive response and then intelligent design. And actually, Had, you've answered most of this question, so I'm gonna start with Luca this time. When you're starting your design process and you're making a mathematical model, where do you start in selecting the parameters that you want? Is it because of a project, or is it sort of something that came out of another sort of research that came? Where is usually your starting point for something that is like the
I mean, our approach is that, I mean, every space has a different usage compared to another one. And if you want to use a space for a certain thing, then kind of we know, not because just we know, but because there have been a lot of research before, what is most important for that space to deliver from an acoustic point of view. So, and the other thing that I noticed that it happens to almost all the specialists in something, to my friends in lighting design, for people working in fire protection. So when they enter a building, their mind is really always focused on their subject. They almost forget about, they put the acoustic goggles, they see the space like that, forgetting about everything else. So every time you enter a space, your brain is thinking, okay, what's different here? How does it sound? So a lot of decisions are based also on experience. In a way, to be able to design a good opera house or concert hall where you really need a lot of personal experience. You need to see a lot of places and hear them, because we have these nice, in a way, from a mathematical point of view, descriptors of the sound in a space, but that doesn't really tell 100% of the story. This is the reason why we have the sound lab and we listen to the thing. So we do the acoustic simulation and we see the results. Okay, they are within a certain ranges that is good for us to say, okay, it can work. But then from the point, a certain sound with kind of the same descriptor, mathematical descriptor, can sound, that the sound can be totally different. So at the end, it's like the baby. We don't know how the baby can build the image on itself, but we do more or less the same. It's something that you get to learn without knowing how, in a way.
So it sounds like you might need to have the simulators learn. So obviously the simulator is missing something, right?
Yeah.
The simulator predicts that these different things sound the same, but for you they don't sound the same. It means the simulator is missing something that's important.
Yeah, the problem is that we could work the other way around, meaning we know, I mean, like starting from the acoustic fingerprints of the room. If we knew which was the best acoustic fingerprints for a certain usage, then we could design a software to come up with the room.
Yes.
But unfortunately, we are really subjective, and there are people listening to music and they have a certain tasting in a certain room, and they think that another one doesn't sound that good, so it's really difficult to define which is the target. It's not like structural engineer. We know that the bridge is to be safe and it doesn't have to collapse. With acoustics, the boundary is really doesn't exist.
There's
So,
aesthetics involved.
yeah.
Okay, so can I move on my questions? I've been struggling with how to program about the higher intelligence or smartness. So, for example, the performance is really easy to describe straightforward. For example, the responses we can write just if or blah 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 blah. But do you have any strategy for higher intelligence or something? Maybe in your case you showed us about the strategy to connect the physical model and virtual model. Both. You can start.
Okay, well, I thought you would, and I don't have time to think about what I'm going to say. So I think programming these things is, as the blueprints become more sophisticated, programming and designing becomes more difficult. So if it's just a static drawing, it's straightforward, but when it's this optimization, like you say, it becomes more complex, and that's where you need more sophisticated tools, optimization tools that will allow you to start with the high level functionality, kind of hit enter and get the optimal design that performs it. So it becomes a kind of optimization problem. But I guess you're asking what happens when some of the design criteria are not quantitative and are difficult to program, like the acoustic criteria that you described. What we've been doing, at least in the lab, is is learning users' perceptions of aesthetics from their interaction. So for example, you can go to this website which we've made called endlessforms.com, and you have this notion, let's say, of that you want to design a lampshade again. It begins, but you don't know CAD, you don't know how to describe it, you don't know anything how to program. But what it does, it starts by showing you random shapes, and you say, this is good, this is bad, this is a bit less worse than that, and so forth. You give it a little bit of feedback, and then it takes all that feedback, and from that it tries to learn what you have in your mind. And then it comes back with new shapes. And then you say, I like this, I don't like that, I don't like that, and those I don't care about. And from those inputs, it again learns and produces even better. And after a couple of generations like that, it begins to produce lampshades. And even though you don't know anything about programming, you don't know anything about quantitatively specifying what you're looking for, it will begin to produce what you want because it can learn from what you're pointing at. So of course, it's difficult to design a bridge that way with all the details, but at least some things you can do that way. So I think that's also a way that you can do acoustics, for example, which are difficult to quantify what you like and what you don't like. And it's a way of programming these things beyond just if statements. And especially for the new types of users that are not trained in programming. Designers that are not trained in programming or not interested in programming. There's more and more people that are untrained but want to design, and that's, I think, the way it's going to work. There are right now 3 million shapes designed on endless forms using that technique.
So it's kind of based on common taste. I mean, it's based on a big number of people that are kind of going to the website and give you feedback.
Yeah, or if, you know, it could be on your taste. If it's just you and you're working on, or a group of people or whatever. So you can.
I mean, in a way, our acoustic parameters, they come from statistical analysis of subjective data and the comparison of subjective data with real measurement in the room. So statistically, I don't know, people seems to like more when a certain parameter is between a certain range. So in a way, it's similar to your approach where you use the kind of the unknown knowledge of people in kind of giving you feedback about a system that is a black box. Basically.
So you can think about that as programming. I mean, I think that's a higher level of programming. Instead of typing code, if statements and loops, you just say, this I like, this I don't like, this is so-so, this is really good. And from that input, maybe one person, maybe multiple people, you can basically program a system so it knows how to behave. Now it's your turn.
Thanks. Yeah, this approach, I think I mean, what I usually do, the programming that I use, unfortunately, it's really static, because it does perform the same task in a limit, always in the same way. I mean, it's an evolving system, but still it doesn't evolve on its own. That is the problem that it would be nice to address, or to have a software that kind of changes itself in order to solve better a certain problem. But in a way, I think there are people that don't like to program, people that are very much into programming, and there are people in the middle, you know. So I think I kind of like in the middle, and it's a bit difficult at a certain point to go deeper somewhere and be able to get the most out of it. Also because, I mean, in an office where you have limited times for project and stuff like this, a lot of time you find yourself rushing out and doing stuff and things.
So I'm going to just expand. This next question is close to it, but I'd like to expand a little bit about the idea of a self-image. We as humans get our self-image from how people look at us, and also how we fit on our clothes, but mostly how people react to us, and that's how we sort of create our own lack of or self-esteem. So the question is, for a system that we're creating, for people that are in between coders and non-coders, can we use these statistical analysis to create a space that has a character? It's hip or it's formal. Can we code something like that? And if we can, how do we start from there?
In my opinion, you can, as you were saying before, the coding of the simulation that was on a PC was based on a really simplified model, a much more simplified model compared to the real life. That is a bit what we do. I mean, all this ray tracing is not really describing really how sounds work, because depending on the frequency that's going to change. But that would take too much time for us to program and to get the results out of it. So in a way, at this point in time, I think that the subjectiveness of people and the people working on stuff is required to make things work. So coding is not enough for me at the moment to replace completely.
Do you use
ourselves.
are the people that are making the subjectiveness comes from the people that are making the code, or the people that the code is made for?
No, I mean the subjectiveness, like I don't know, when you work on a certain project, you can do programming, coding, and optimization and stuff like that. But as you said, is it possible to build spaces with character? It's in a way behind. It's too far from what at least I can do with programming. I don't know if it's possible, but it looks to me that programming at the moment is good to get quick answers and that are fairly reliable, and then we will take a view on that.
I have no clue how to do it. I mean,
Okay, so this is beyond.
Well, I think in general you might want to have a system that is able to sense whether people think it's hip, like you said,
Yeah.
and adapt to maximize its hipness. But that's a very engineering way of looking at it. But that's really, again, if you look back at, let's say, this endless forms project that we're doing, people are trying to design, let's say, perfume bottles there, and the machine is trying to learn what people like and what people don't like. And in a way, it's a small case of what you were asking. So how do you, so that's a very simple, small object that is trying to aesthetically please designers who just give a thumbs up or thumbs down. But you can take that principle and apply that to larger objects. For example, you can imagine, I don't know, a car maker starting off with standard car shapes and letting people vote thumbs up, thumbs down on what's cool and not cool, and gradually the machine will generate better and better car forms that please more and more people. And you can imagine that with buildings. I mean, I think conceptually it's the same thing, although it's much more complicated.
Now, the thing that I'm a bit scared about is that what if we end up having this wonderful system that gives us the answer, okay? And but it's a magical thing, you know. But what if then we end up having one answer? Then this kind of magical place will be just boring, you know. So it's.
So if it's boring, then you give it thumbs down.
Yeah.
And then it becomes something else.
Sort
Yeah,
of like the
Because it's the
Pandora.
human is in the loop. We're in the loop here in this case. So we'll start.
Yeah, but yeah, in a way, the subjective feedback has always to be taken in account, because if not, if you stop with the subjective feedback, then you end up focusing your shape towards converging somewhere.
Yeah.
While, as we can see in architecture, in design, or whatever thing, shapes of building, the way we use building is something that changes. In 10 years' time, it will be different as it was different 10 years ago. So that's something that is to be updated with the system.
So, yeah. Okay.
Part of it is our sense of aesthetics is changing over time, and the technology, construction, and all that. So it's all changing.
I mean, there's an argument that I mean, I'm not gonna start talking. This should start next, but there's an argument that aesthetics can be mathematically quantifiable, but for the technical term, hip is not really quantifiable. But if the occupancy is hip, then they will keep doing the thumbs up. If someone that is a little older and doesn't like this kind of what's going on, then they would be giving the thumbs down or whatever, reacting to it, and then it depends on the back and forth. So it's sort of like for lack of a better example, Pandora, where you say, I like this song,
Yep.
and you sort of change the genome, and then you don't like it, so they know that this is what you don't like, and then you just make your own radio. Sort of.
Yeah.
Yeah,
it's-
but what if tomorrow we'll change the idea? and I
If you
get-
if you change your mind, it adapts
it's
back.
out there, yeah.
You find a track that you didn't like that comes back to you. So I don't know if it's a glitch or it's by design. Do you want to go ahead?
Yeah. What I wanted to ask is about reproducing by myself the robot or system itself, because the traditionally architecture is static. Architecture was static, but recent days it's getting more emergent. What should I say? The question is, do you have any strategy about reproduction of the system, or any idea about autopoiesis or something like this kind?
About about self-reproduction of. So that's something I didn't talk about at all. It kind of has to do with the manufacturing side. Certainly we've been exploring this idea of machines making machines. The robots that don't just adapt in their behavior, but also adapt in their physical structure. So can you have a robot that can grow a arm when it needs to, or if a arm is missing, it can, it needs to do a new task and grow an extra arm, or can, do those kinds of things. And we end up, so we've tried to do that many times, and we built all kinds of systems that are basically, in the end of the day, they're always modular. So you end up having systems that are made of lots and lots of components and then these components can be rearranged, or the robot can rearrange its own components to reach, to become something different physically. So that's kind of the only way that we found to do that. We have made a robot that can construct another robot from basic pieces, and we're working now on making a robot that, you know, like two robots that can walk up to a third robot, take it apart, and make themselves bigger for those pieces. So these are kind of machine metabolism ideas. So watch out for that. Your printer walking up to a fax machine, taking it apart and making itself bigger. But there's so how that applies to buildings, I mean, that's a nightmare I don't want to even think about. But that's a good theme for a movie, actually.
I don't know, I mean, thinking about this and applying it to building, I would think that maybe in the future we will have a building with, I mean, integrated so much with technology that it will say to us, suggesting us, look, you should put another layer of glazing outside because here we are losing so much heat, you know? And so it's not that the building maybe will be able to reproduce or to add one arm, but it will suggest to the user, look here, there's something that doesn't work because my sensor is telling me that there is a leakage or there is something that doesn't work. So a better interaction between the building and the user, that kind of a sort of dialogue between them would be good.
Yeah, that would be.
That's a lot safer.
Yes.
Maybe next question is connected to this topic, I think.
Yes. Where were we? Okay. Yeah. That is. I mean, I don't want to. I would like to go into this thing about their feedback. If you have two intelligent things, you have a building that is intelligent or a design that's intelligent, and then you have a human that is supposedly intelligent. And how do you observe something like this? Do you observe the actual design, or do you observe the human, and do you evaluate depending on the human, or do you evaluate depending on the performance of the actual design?
From my point of view, as I was said before, it's a dual evaluation, because when we look at the results from the machine and the numbers, that is just something that be done just by the machine. So checking if the numbers of the acoustics or anything else are within certain tolerances. And when we listen to the place, then the machine doesn't know how to do that. And so we rely on ourselves, our supposedly intelligent people. But I think, you know, as people say, a genius is maybe 1% genius and 99% sweat. So I think that people can train in a way to be more intelligent, or at least more aware and pay more attention to things around them.
So we can start. Okay, we're being. So we're just gonna wrap that up, I guess. But do you want to ask the last question about the intelligence and smartness?
Oh,
if we can
I've already asked.
Yeah. Okay.
Yep, saved by the bell.
Saved by the bell, right? Okay. So we are thankful, and thank you so much for this really cool discussion. I don't know. I forgot that there's people on the other side. So I would like to thank you guys for listening to us, and we don't have time for questions, but if you hang around after the third session, you'll be able to ask them all the questions your heart desires. We will take a lunch break until 2, and we will come back promptly. 10 to 2, yes, sorry. So 10 to 2, Brett will make an introduction for the rest of the day, and he will give a little 5-minute talk, and then we will start our next session with Francisca and Arturo. Okay, thank you.